Hello, basement hackers. Gonna get started streaming for tonight's stream for Sunday, the 26th. Um, Today we're gonna dive more into the Quick Emulator with embedded ARM M4 software and the GCC example projects. We're gonna get them running on there without a Linux operating system. So the goal is to get them running, understand how the TI machine is working. Some of that we're gonna have to rebuild our knowledge because we didn't save some of those scripts. So we'll make some scripts around handling like running ARM GCC to compile, which we're using the make system, make file system that was already with their example projects, but we're going to script just passing in the arguments we need, and then also kicking off the emulator. And then if we get to it, we're going to try to hook GDB to it and debug from before the first instruction is executed. We'll step through code, and there's going to be some figuring out linker stuff. We might have to edit some linker scripts. Um, and yeah, so that's kind of the goal for today. So let me switch over. I just want to make sure you guys can all hear me properly. We'll step through code. Yep. Okay, good. So let me switch over to coding. All right, sorry about that. It should be fixed now. Just trying to confirm really quick. Do you hear any sound? Testing. All right, sorry about that. Yep, got sounds. All right, sorry. I was just explaining some of what's installed and all that. I noticed that the provisioning script was not properly did not properly install some of this, so I'm just gonna make sure that this step ran, because that's how you get the quick emulator. And it looks like it didn't install the quick emulator. I had to rerun my setup I wanted to test it, and it seemed like there is still problems. I'm not going to waste time today on that, though. Let's just get this installed and start working with a quick emulator. Sorry about the sound problems. I'm still learning the tools to stream properly and get it set up. What I was saying earlier is any feedback on that, just let me know. Yeah, I should be using the right microphone. I think in prior streams I was using my webcam mic by accident, and that microphone's not good. Like, I have a dedicated USB blue snowball. That's really nice. It's meant for podcasts and stuff like that. I've had it for a few years. They have newer generations of them, but it works well. I'm like a few feet away, and it should be picking up pretty good. So once this installs the quick emulator, we'll just try to run like we ran last time. So we're in the sample app. We should have make now, so let's do a make clean. And what is this complaining about? Am I not in the right folder? Yeah, there's no make file in here. I think it's in one folder up. Yeah, so this will make it for all the projects. Each of those blue, is that blue or purple? Let's say purple folders are folders that have a project. And then there's a root make file that will run all of them, and it'll run the make. Each of them has their own make files as well. So we'll do make clean. What did it not like? Unfortunately, I have the wrong permissions on this, so we're gonna just hack around a little bit, and we're gonna chown it to the vagrant owner, and capital R, and sudo. All right, that should help. Samples. Source. Oops. Well, a little fast, but I'm just trying to get back to where we were. So make clean. Oh, I think it's doing it. It's just that because of the wrapping, it just looked like it was not, and it looked like it was like a lot of error messages. But it was just saying entering a directory, one of the projects, cleaning it, doing the next, leaving it, then entering the next one. So if I do make with Cortex. Cortex M equals 4, this will make it for all the, so this is compiling each of them. So let's go into now the quick emulator example project. Now last time what we looked at was that the make file doesn't do, if you compare the make files of this project and the one of the minimum, some of the things that were different were the minimum says that the startup should clear BSS, but also that your entry point should be main, where ours doesn't have an entry point because we're expecting that the code is going to start executing at instruction address 0. So there's no like reset that's going to jump into us. And some of that I need to understand more, and we're going to go dive into the machine that we're using and try to understand. So we're using a TI one. So let's look at the quick emulator, and let's try to get that command to fail the way we had it failing last time at least. So, because I didn't write a lot of that down, I could go look at it, but the source of knowledge that we were using was from this guy, and we pretty much built our way towards what he was doing. So we do want a binary image. What do we have now? So we do need to do object copy. I don't know. You might be able to pass it an AXF file, but I'm not sure. They're doing binary, and that's what I expected to do. So I know it's iHex for Intel hex format. The in file is going to be this hello CM AXF, and the out file is going to be hello CM4.hex. Oh wait, we said bin, didn't we? We'll make the hex and then we'll go make the bin. But now I have to remember how to object copy to bin again. What's the name of it? They say all the supported ones down here, and binary is one of them. Okay. So let's go and make the -O is what format we're going to output, and we're going to do binary, and we'll make that a bin file. So now we have those other files. So when I run the quick emulator now, I'm on the in the terminal still. We're gonna run system arm. So he does some of that. Like he compiles, then he says what machine he's gonna be compiling for. So this one he does -G, and what's -G? These two together are to compile. He's doing the startup code first, and then he's making a startup.o. Then he's linking them together. So he's compiling his startup code separate from his test example code. And his startup code is this file that pretty much just sets the reset vector. This is his linker file, which he's going to have this .o file for his startup.s. He's going to reference that right here in his linker file. And they're going to this offset because he thinks that the machine resets to this other address, and that's where he wants his startup code to be. And then the startup code goes to C entry, is where it's going to branch to, and this label is in his code. Where is it? Is the name of one of his functions. So it should call that function right there. So his reset guy is going to be at that address. He's going to link in that startup. The only thing I don't see reference, reset is the entry. And then it's going to keep doing that over and over, calling that guy, and that's him. So we're not doing that linking stuff yet. We're just building a binary that doesn't have any special linking. So if we look at the compile statement, there was no extra linker script passed in, and we saw that from our makefile. Yeah, there's the name is the name right here. Hello. These all are broken down from this library they have here that's up in the one folder up. But pretty much they normally would specify a linker script on this line, or in maybe the map file. But this just says to make a map file, because you tell GCC to spit out a map file, which tells you how everything was laid out. This one says, I think it's an optimization flag, but I forget. They turn on nanolib and semi-hosting, but that's it. There's nothing else added in. And this just references GCC. And they make this file name and reference that right here. Or is that right here? Okay. So let's do QEmulator. System arm. And I just need to go through the help again. Actually, we're going to do what he did, because I think by the end we were aligning with his. So we weren't using the same machine, and there is a way to print the machines out. That's what I need to look up again. I'm actually going to full screen this for a second, because we're going to have to do a few commands. So how do I list out the machines? Actually, let's do the man page. List available. Select the emulator by name, use machine help. Yeah, we want to do this, and the same thing. There's also for like the CPU or something, and that was a little bit confusing to me last time. But like, what's the difference of the machine and the CPU? I mean, yeah, the CPU can be a specific, like processor or something like that, but you'll see, it was like one's like a family, and like this one is. We ended up going with. We looked online, and these two are the ones that we had to go with, and I have that up in here. There are two TI chips. That they're these two TI chips. So let's write these down in a notepad. Oops, I hate this console. I keep putting it off, but I need to get a better console. These are the two chips, and I think we said the higher number one had better peripherals and stuff, so we were gonna. I don't know how many of them are emulated, but they sounded better. And I think the other one was just the CPU help. Oh yeah, but you had to specify what machine. So dash capital M, and we're gonna paste in. Oh, that didn't work. We're gonna paste in. Why is it doing that? Windows is really weird to me now that I've been on Mac so long and Linux. So here's all the CPUs for this machine, and we want this guy. So we'll just copy this list. We can keep it in our handy dandy notebook. So undo that. So if I do that and then I paste in our Cortex M4, now it says there's no kernel. So cool. Now let's add in our kernel is going to be our binary image, binary file image, our bin file, and then could not instantiate. Oh yeah, because it expects that you're gonna not be headless. So there was his thing had it. So I'm just gonna steal it from him versus trying to look it up. There's no graphics. These two we don't need yet, but they had to do with GDB, and the capital S says to start a network GDB server, and the other one said to break before you execute your first line, and that the two together allow you to then attach to the GDB server running in this in the emulator, and then from then when you attach, it hasn't executed anything, and then you can start stepping and stuff. So we want the no graphics though. Oh, and I think we saw that the default was 128 meg, so I'm just gonna leave it. If we find problems with it later, we'll change it. But the default's fine. So now I tried to execute, but I got a hard fault. So this is kind of where we left off last time. So now we need to figure out what is special about this machine. And because the example that we're looking at, the guy was using a different machine, not from TI, from ARM themselves, but that wasn't in our list of supported, so I don't know if it's because of the QEMulator on Linux or the version I have, or if it just changed after 10 years, because his example is from 10 years ago. So yeah, if we just scroll back up to that list of supported machines, you'll see that there is no versatile PB that I saw. There's these virtual ones. Actually, there is versatile PB right here, but I think it didn't have Cortex M4 is part of the problem. Let's go to where we were listing out. Oops. I want to list it out for versatile PB. Oh, it does have Cortex M4. Why didn't we do that last time? Did I miss it? Let's actually go with theirs. I would like to try TI's afterwards, because I do think I can get a TI dev kit and we can start linking for the actual hardware versus the emulator, and it would be fun just to go back and forth, write totally automated testing in the emulator, and then run the same code on real hardware with very little differences, if any at all. It may be just only linking, and you might even be able to have them so they link exactly the same depending on how the emulators work. So let's try versatile PB with our binary. We already know that it's not going to work right because he's doing stuff that was not right. Versatile PB. I know I spelled that wrong. You don't have to tell me, chat. Versatile. Yeah, versatile. Versatile PB. And what did his command? What's the casing on that? It doesn't matter. Let's see his commands. Versatile PB. Okay. So let's try that. Now, I wonder if, because we switched to a different machine, if the default memory is going to be the same. So what did this guy say? We tried to run the binary. That's interesting. We only compile telling GCC that we're compiling for Cortex M4. And that would make sense. You wouldn't have to compile any differently, other than you're going to have libraries for that specific chip for anything specific to the peripherals of it. Like if you're going to have like an I2C thing, there's going to be some type of CMSys to map that, and anything that's specific to that family would, of course, be custom libraries you're going to have to compile with and link with. So there shouldn't be any actual GCC level of differences unless there was libraries that were using different types of symbols and pragma compile flags and stuff that you had to pass in. But we're going bare bones right now. So what was the main thing? Pulse audio. So this is trying to do load some audio stuff. What else did he have? He had size, and then he had the GDB stuff. And he talks about but he had ELF files. I mean, mine are ELF files. They're just not called ELF. But that shouldn't matter. So let's try to do some of what he has here, where he's making the startup script, and we'll do that and make a linker script in here and edit their sample application so it works for this guy. So we're going to make startup.s. Is it capital S? No, it's little. Capital S would mean that there's a preprocessor needs to run on this assembly file. Paste. Do I need a new line at the end of this? I usually like adding new lines at the end in case I cat it or something like that, and keeps everything separated. Let's go and now make the LD script as a linker script. Why is it D and not like LS? It should be a linker script though. Linker directive? No. And I'm just trying to use the same names as him. Alright, so let's paste this as well. And I'll add my new line. Now, in his startup code, he calls that other entry point. So we're going to need to edit their hello world and recompile so that it has that entry. So instead of calling it main, and instead of having a int return type, we are going to call it this guy. Now what do they do? In his code, he does a while the string being passed to this print is not a null character, then oh yeah, he's doing some mapping to the UART. So we will need that as well. I hate the paste or this terminal so bad. Like, no one's gonna hit insert. I'm sorry. I've not used insert ever, and I use a computer all the time. It's just in the worst location possible. I don't care about their printing Actually, I do. Because... It's almost like I'm not even using the actual Hello World that's in here. But... like, this is just terribly formatted. What is this font that is... like, this is the weirdest star font. And C entry. And they... So pretty much we're just taking what they have. Okay, we can get rid of this include. So it's pretty much exact. Let's just make it exactly what they have. All right. Make clean. So I want to make for Cortex M4, but we need to edit the make file. So let's see, for the linker flags, but we need to compile an extra file too. I think I just added to the end here. I need a startup.s, and I need a link for the linker flags. I'll put it here, I guess. We need to, I think it's capital L. Let's go to the man page for GCC to look for what that is. Actually, we could probably look in the one right above this, the makefile .conf. They're probably doing it somewhere. I was expecting to see we could do this startup. If we set the startup, where's this referenced? So I want to look at one of the other examples. Yeah, it's -L. Oh, but it's T for the actual file. You're just saying where to look for the linker script. So we're going to do this when we run it with the linker script being there. And then they do that as part of LD scripts, but they're just putting it in here. So we could do a similar thing. Where do they do the start? And they put startup there. Okay, so we did that, but we just didn't make a variable for it. And we'll do the same thing for the -T and -L. So append A is to move one, insert. So and it's called test.ld. I was following his, so that's why I'm, yeah, test.ld. Let's see if that works. So make Cortex _M equals 3. Oh, 4. Similar message, LO register required. Yeah, so why was his not needing that? And it does make sense that you would need the stack and stuff, the size of it. was just trying to look to see if his was defining it anywhere. Where's stack top? It's defined right there. So what is it complaining about? Optimized for size. Compiling those two guys with thumb instruction set for the Cortex M4. Link time optimization. These are just like designated sections for those. Use the nanolib for making a better for embedded. This is for semi-hosting. This is for size. Spit out a map. Look in the current directory for linker scripts. Look for link with that linker script, and the output file should be that. So why? So then it said assembler message when it was trying to compile the startup on line 3. It said LO register required. So let's look at. We can't look at it in our text editor. So let's just edit it by hand. Startup line 3. It said LO. Required. What did he use for compiling? Oh, he did a different ARM. Different CPU. I'm wondering if that's the main issue. Just SG do again. Oh, it has symbols. That's what it is. Because he's going to debug it, so you would need that for GDB to put all the debug symbols in. -C says to compile. The first one, oh, he's literally running the assembler separately. So I'm wondering if that's what we need to do. But it being an ARM on the 928 EJS. Because we're doing Cortex M4. I'd have to change this too radically to do that separately. Actually, I might be able to, can I just make this .o and do my make knowledge is a little bit lacking. I'm just going to follow the pattern, see if I can get it to work. So they have CC here. Where's CC? Right here, but they don't have the ASM. So you know what, I'm just going to copy this and where's the AS? Let's do AS. And we're just going to, we're going to What's in the C flags? C flags, arch flags, startup defs, could throw the C flags in here. That'll get us. I don't know if the CPU is still going to be a problem. Let's see if this runs though. No rule to make target. What is make talking about? I'm not good at make, because on the next line, it says that it has the exact same type of thing. It has this C file. Oh, it's .s. Let's just steal some of them. It doesn't want these. Let's do arch flags. Did I spell it right? Alright, let's try to run this again. Assembler message cannot read from standard input. Resource temporarily unavailable. I don't know why I'm getting alerts. Why didn't I put the file in the end? Oh, I did it. Oh, oops. I must need $at. What's $caret? Oh no, $caret is this. $at is this. So I kind of want both. Do I want it in that order? I need a dash O on that. Oh, yeah, that's exactly what it is. For the out file. So that looks better. Compiling this, I mean, this could really come after the flags. So I broke them apart, but it didn't. It still has the same error. So LO register required. That's not what I wanted to do at all, but it's on my clipboard. We can trust this guy for a second, but he's saying that it's a thumb instruction set, and they do work for me, as you could see from my screen. Yeah, let's give it a shot. Did something better that time. Let me just delete my startup bin. I need to add to my clean. I'm just going to do that actually. Clean star.bin star.hex and star.o for object files. Make clean. What do we got in here now? Linker script, startup code, assembly, and hello.c in the makefile. That's what we want as our clean. Now I got the .o, but I didn't run the next one. Oh, does make just run the first target if you don't specify one? So I need to make that dependent on that or something. And that is my default. I remember something like that. Like it's only running this target, it's not running this one as well. Because it didn't make an AXF, right? Yeah. How do I do that? Let me look at make file, set default. Oh, yeah, you do something like that, and then you say it depends on the other guys. So maybe if I just move it below, it should do it. Ah, shit. Damn it, I can never get the new lines right. My copy. Let's do it clean and make sure that it's all working right now. We should probably move this into our project, but so now we have an AXF file. Let's actually also make it do an object copy for us, for the fun of it. So we're gonna make it use the name. So I'm just like learning make without looking up how to do make. I'm trial and error. So we're gonna make a bin file because that's what we're gonna work with. Yeah, let's just throw core in the name. .bin. It's gonna be dependent on this John here. Probably could make a new variable for that, but it's gonna be dependent on him, so it'll cause him and they down the list, and they'll make that happen. But we're gonna do an object copy, which we're probably gonna want another one of these, but with object copy on the end. Object copy, and I already can't remember if that's correct. Yep. Wasn't sure if there was a an O in CPY, or if they abbreviate, like shorthand it. Okay, so now I can hear. Yeah, I need to change that variable. We'll do OC for OC. I don't know. Is there a shorthand that people normally use? We're going to use OC, but someone tell me in chat if there's a better one than OC for object copy. And we already know it's dash O for the output type is binary, and then the input's going to be the AXF file. So we should make a name for this. I feel like it's being used all over the place. Copy him, open. Let's do like I need to uninstall this crap. Yeah, that's great. Show off all my stuff. Alright, so of course. Windows loves me. Okay, let's just say binary name. It's not binary though, it's like executable name, exe name, whatever. Because we literally have a bin file, so I don't really want to call it binary name. Okay, so now it's that, and we can change this guy to be that too. And then we need to say our input file is going to be that guy. Paste. Okay, so now that we have that as our input file, and our output name should be, this is going to be a bin file. So it's like I should have a name, and then I should have whatever. This will work. Let's try it. Clean. Build. I got a binary. See, it worked. I didn't even have a typo. That's how good I am. Alright. Quick emulator. Let's try to run this guy again. We're going to run it with his. So we said capital M is going to be his machine, which we have listed, and I did not save it. So let's just do help. And that was called, it was this guy right here. They actually have another one. We did see that last time, but there was a reason we didn't go for it, and I don't remember what it is. So list this as our machine. The machine. For the CPU, still want Cortex M4, but what is he putting? Because I know he's compiling different, and at some point it's going to be our fault when it doesn't work. Right here. It's because he compiles with this and not Cortex M4. He doesn't set the CPU. I wonder how that works. Maybe because it's already compiled in. Alright, well, I'm going to try it this way. And then we didn't need that no graphics. Is it 2 dashes? No, it's 1. Graphic. And then the kernel needs to be our hello CM bin. What am I missing? Anything? Let's try it. Invalid option. Where do I have a dash C? Oh, I think it's CPU. Oops. Alright, so I know ALSA and is also audio stuff. Why is it trying to do all this audio? Maybe because I said Cortex M4 and not let it do what his did. Let's try to get his working exactly how it's supposed to first. So if we got rid of this, it's closer to his, but we need to compile correctly. So, it's actually not, it didn't segfault that time. It's actually running right now. All the ELSA stuff failed, but so I'm in the quick emulator. I did Control A C. I think he mentioned it, and I saw it somewhere else. Yeah, or it's X. Oh, that's how you exit. So I did C. Like I would be in a screen. So that terminated it. So it's actually running. Yeah, I don't know what all this audio stuff is. Tried to set up some type of DAC, digital analog converter for the audio. And there's a bunch of libraries. You cannot find cards and stuff. That's weird. Now I can't get the prompt like I did last time. I can't even get it to abandon it. Control A. Control A, X. Control A, Control X. I know his is when it's using GDB though, so. But I just had that happen. Oh, caps lock's on. Maybe not. Control Alt F? I wonder if you could say no new audio. Can't even get it to break out of it now. Hmm. I'm gonna try to log in with another shell. What? In the VM. How is it saying there's no VM? What? Am I in the wrong one? Do you not have two shells? Sure, you do. Alright, that's not gonna do what I want it to do. Kill my shell because I can't get it unlocked. I was trying to what he was suggesting and other people. What? I was literally just in it. How is that even possible? No, that's the opposite of what I want. Why is VirtualBox not coming up? Just stop right now. Oh my. You could have started any other program on my entire machine and it would have been better than starting that. This is like a beast. Probably wants to go update and stuff. Alright, yeah, why is VirtualBox not coming up? Let me get that running again. So I do want to understand I want to look for the documentation for some of these different machines. ARM versatile boards, AB and PB. The ARM versatile baseboard is emulated with the following devices. So he was using this ARM 926E. So even though it listed the CPU, I think the reason it was having problems is because the CPU... Oh, I wonder if I crashed it before. Is that why I need to up it again? I wonder if that's what happened. So Cortex M4 is not even in this list. Let's do this quick background on QEMU while that's starting up. So you can download and uncompress a PC hard to your hard disk, an image, a Linux image, should boot and give you a prompt. So this is running a little differently. We're doing ARM and we're not trying to boot Linux. Invocation. So you give options and they're optional. And the image is a raw hard disk image for an IDE. So there's a version, help menu. You can specify the name with some stuff. This is all things we saw. CPU, the image, you can specify VM port for enables emulation of VMware IO ports, VM mouse, etc. Dump guest core. A lot of this would have to work with the image that you're running, but we're doing embedded image, so probably don't need any of that. So right, this is used to enable an accelerator, depending on the target architecture, KVM. We don't need any of that. SMP. Is this Samba? No. Simulate an SMP system. Yeah, we don't need that. Size of the memory. Mempath. Is there a way to disable audio? Audio help will show the audio dev equivalent of the current specified environment variables. It's deprecated though. Maybe I could just say none. So these look like flags that are specific to certain devices. Putting block devices onto the file system. So a lot of this is for when you're running Linux and not embedded. Display options. We want no graphics. Simulator to block devices, character devices. Let me just search this for okay, so I mean this is just the main page, but so this is what I wanted a second ago. Control and Alt. How did I get it the first time? Did I accidentally hit that? Oh, full screen, enlarge, shrink, restore. But when it's headless, how do I exit? In the graphical front end. Keys in the character back end. Okay, Control A, X. That's what I was trying to do. It wasn't letting me. I think it's because it crashed. It literally crashed. Control A, H for help. S to save disk data back to file. Console timestamp. Alright, so we can have this open as a cheat sheet. Disk images, networking. Where's sound? Because I just want to make sure that we could turn off sound. TLS, GDB usage. So he talks about using those two S flags. See, like they're doing like an actual Linux image. Oh, here you go. This is a good breakdown. QEMU can emulate both 32 and 64-bit ARM CPUs using the AMD Arch 64 one. Executes a 64-bit one. You can use the ARM or that one to do a 32-bit one. In general, command lines that work with system ARM will behave the same when used with Arch 64. The Quick Emulator has generally good support for ARM guests. It has support for nearly 50 different machines. The reason we support so many is that ARM hardware is much more widely varying than x86 hardware. ARM CPUs are generally built into SoCs, system on chip, designs created by many different companies with different devices, and these SoCs are then built into machines which can vary still further even if they use the same SoC. Even with 50 boards, Quick Emulator does not cover more than a small fraction of the ARM hardware ecosystem. The situation for the 64-bit ARM is fairly similar, except that we don't implement so many different machines. Okay. Choosing a board model. For Quick Emulator ARM system emulation, you can specify which board model you want to use with -M, or you can spell it out. There's no default. Because ARM systems differ so much and in fundamental ways, that's why I had to, when I did the CPU, it was like, well, you gotta tell me which machine. Typically, operating system or firmware images intended to run on one machine will not run at all on any other. This is often surprising for new users who are used to the x86 world, where every system looks like a standard PC. Once the kernel has booted, most user space software cares much less about the details of the hardware. If you already have a system image or a kernel that works on hardware, and you want to boot with Quick Emulator, check whether Quick Emulator lists that machine in its help menu. And we saw which ones they had. If it is listed, then you could probably use the board model. If it is not listed, then unfortunately your image will almost certainly not boot on Quick Emulator. You might be able to extract the file system and use that with a standard kernel which boots on the system. If you don't care about reproducing the idiosyncrasies of a particular bit of hardware, such as a small amount of RAM, no PCI, or other hard disk, etc., just run Linux. The best option is to use the virtual board. Okay, so this is a platform which doesn't correspond to any real hardware and is designed for use in virtual machines. You'll need to compile Linux. Yeah, well, we're trying to do raw stuff. So specific board documentation. So this is kind of where I was trying to lead to. So they do for the versatile board. Now where's the one from TI? Let's open both of these up so we can compare them. And so then ARM CPU features. This is good stuff. This is the stuff I was hoping to look at. So we don't want this guy, we want this guy to start because it's going to follow. And this is kind of where we landed on originally. If I go back to this guy, emulation includes the following devices. So these are just M3s as well. So neither of them spell out M4, even though they have it in the list. But I'm wondering if it actually does. Timers, UARTs, analog to digital converter, I2C interface. Timers, UARTs, ADC, I2C, SSI interface. This guy's more flash and SRAM. What's an SSI? Okay. Oh yeah. All right. It also really doesn't say much about the actual layout of it. So how do I get to that? ARM CPU features. CPU features are optional features that the CPU of supporting type may choose to implement or not. In the Quick Emulator, optional CPU features have corresponding Boolean CPU properties that, when enabled, indicate that the feature is implemented, and conversely, just when disabled, indicate that it's not implemented. An example of an ARM CPU feature is the performance monitoring unit. Okay. CPU types such as those which respectively implement ARM architecture references. As not all CPU types support all optional CPU features, then whether or not a CPU properly exists depends on the CPU type. Alright, well, what are some of the features? So this is where they're turning on and off features. How do you just print them out? That's all on that page. System mode emulation. It's possible to create a VM that pause. That's capital S. Somehow my Vagrant machine just got destroyed, like messed up. Well, hopefully that comes up soon so that we could try some of this. Going back to his, for versatile, it explains why it's doing that. Now, why does it say it supports a Cortex M4? Now, a 3 and a 4 are not that radically different. So this guy's trying to do an interrupt vector table. That guy's still chugging away. Let's see if he has any other good information at the top. So this is where he does an interrupt table starting at 0 when he links it. And then he jumps to the reset vector for the rest of the code. Because 1000 hex, I think, was... Bare metal programs run without an operating system beneath. Coding on a bare metal system is useful to deeply understand how hardware architecture works and what happens in the lowest level of an operating system. I wanted to create a simple example of a bare metal application for ARM using free open source tools. Company providing free versions of GNU GCC toolchain for ARM cores, in particular the embedded application binary interface toolchain can be downloaded from them. So he created this hello world and printf. He compiles it for this architecture CPU. In order to create a bare metal program, we must understand what does the processor do when it is switched on. An ARM9 architecture begins to execute code at a determined address that can be 0, usually allocated to RAM, or it can be an offset in, usually allocated for read-only memory. We must put some special code at particular addresses. The interrupt vector table is it is a series of 32-bit instructions that are executed when something special happens. For example, when the ARM core is reset, or when memory contains an unknown instruction that doesn't belong in the ARM instruction set, or when peripheral generates an interrupt. the serial port received a byte. The instructions in the interrupt vector table usually make the processor jump to the code that handles the event. The jump can be done with a branch instruction. So yeah, they're all just branches to somewhere else. Where these are just all branching to this, to doing resets. And then his reset says to reload the top of the stack pointer to the top of the stack, branch literal to this guy, and then this loops infinitely doing that anytime it's reset, anytime this guy returns. Line 1 generates a section name interrupt vector containing executable code. I'm surprised I didn't have to do something like that. Maybe I do. And that might be why I'm having problems. Line 2 exports the name reset to the linker in order to set the program entry point. 3 through 11 is the interrupt vector table that contains a series of branches. B dot means that the code branches on itself and stays there forever. Oh, so this branches to itself. Okay. Line 14 initializes the stack pointer to the top of the stack. 15 calls a C function called centry. Let's see how our machine's doing. I don't know why its virtual block's not coming up. I need to see what's going on with this who makes virtual blocks? Why is everything... That's probably why, because there's like installed on 2 different drives. There are so many instances now. Alright, so going back to what we had, I don't know, the machine has all these problems. So they're linking against the linker script, some test code that's object file, and startup object file. That was the compiled code from earlier on. So they compiled this assembly into an object file, and they compiled this C code into a test.o. So what I want to understand is, like, what documentation should I go to? Should I go straight to, like, Cortex M4, like generic documentation on the startup sequence and where the interrupt vector table is, or do I have to look at the emulators? Like, it's like no notes on this page. Got my shell back, but it's not provisioned. What the hell? Run the provision script again. I don't know what happened. It like crashed my entire machine, and it like lost even like things that were already installed on it and stuff. I think I have like 2 different images being tied to Vagrant. So right now I'm just running my provisioning stuff, which reinstalls GCC ARM. I'm gonna have to hand run just this guy. System address map. The processor contains a bus matrix that arbitrates the processor core and optional debug access port. Memory access to both the external memory system and to the internal system control space and debug components. Priority is always given to the processor. Alright, hold on. Code, SRAM, peripherals, external RAM. Embedded trace macro or whatever. This looks like something good. I wish I could get rid of this huge banner. I'm like, half my screen is just being eaten by stupid stuff. M4 block diagram. That's an vectored interrupt controller. Interrupts and power control. ETM. High available bus for the access port. Instruction fetches from code memory space from 0 to 1 all Fs are performed over the 32-bit high availability bus, light bus. The debugger cannot access this interface. All fetches are word wide. The number of instructions fetched per word depends on the code running on the alignment and the alignment of the code in memory. I kind of want to just... The processor supports 2 modes of operation, thread mode and handler mode. The processor enters thread mode on reset, whereas a result of an exception return. Privileged and unprivileged code can run in thread mode. The processor enters handler mode as a result of an exception. All code is privileged in handler mode. Alright, I got that back. Alright, that stuff's working. And I was just going to paste to let it provision properly. So I kind of want an overview on how it boots up and runs. This is literally every assembly instruction, yeah. cheat sheet. He's using an STM part. He's using Kyle. Doesn't show me that one. Okay. At some point, you should talk about the reset. It's probably so basic that it's not even talking about it. Alright. I lost all my stuff when that crashed. I think it's because it's on a separate VM and it's not getting reloaded properly. trying to explore to see if I can understand how to approach the problem. Because I do want to go to the Intel one if we can, because it did have, well, it said it was also Cortex M3 also. I mean, we could go to an M3. I just wanted to do an M4. Is this versatile? No, this is something else. I could have sworn I just did this, but had make in the list. This is the same guy, right? Yeah. I'm actually going to end stream early today. I'm just not feeling it, and I learned some more, but I just can't get to the point where I'm understanding the emulator and how it lays out memory and the linker. And this is probably me just not understanding the linking of a standard Cortex M processor. So I almost want to do a little research off stream just to understand it a little bit better. Understand that there's going to be like a vector interrupt table. They're going to be able to have like all these handlers, and I've seen before where you'll have weak handlers that like SDKs will define, and then if you define your own, it'll go to your functions or labels or. I just want to understand how it's laid out. I'm going to switch it to just chatting. Yeah, so today was a little tough. I'm going to try to fill in another day this week to try to get moving on a lot of this, because I want to actually start being able to write some code on these, and I want to get a development kit so that I can work with it on real hardware and emulated, and from there I'm going to really be able to debug it and then start spitting stuff over the UART to at least log, or do semi-hosting, or maybe both. That's kind of the goal. We'll get there soon. Alright, well, keep hacking your basements. Hopefully better than I was today, but it was a fun session. Still got some stuff done. When it crashed and lost some of my stuff, that kind of took the sail out the wind. So next time we're going to make some good progress. I'll try to see if I can get on before Tuesday, but if not, I'll see you on Tuesday, and keep hacking your basements.